Welcome, everyone. We're going into carbohydrates again, this time, chapter 13.2. We're going to talk about stereochemistry or chirality. This is a whole new topic that many of you have never seen before, but you're going to recognize it when we use analogies to the human body and other things that you're familiar with. But before we get into that, uh, I always recommend that if you can get a molecular model, which I'm bringing here to your attention. For example, where I have a carbon and four hydrogens um, uh, placed here, where it's a tetrahedral. Remember, we studied geometry of molecules, and this is one example of that, and how that actually looks. And then we have a very simple molecule like hydrochloric acid. Um, where we have the chloride and the hydrogen attached to each other. So that's a very simple model. Very little geometry with that one as opposed to the first one. And then we have something that can be a little bit diversified that has carbon and hydrogen and chlorine, the green molecule representing chlorine, and the white atoms, of course, representing hydrogen. I meant to say green element, green element. So this is a carbon, hydrogen, you got carbon, two hydrogen, and two chlorine. So you could write the formula for that. And you can see the structure is very similar to the first molecule. It's tetrahedral as well. And this happens to be achiral too. Okay, but we'll go deeper into this as we introduce chiral molecules. What are chiral molecules? Well, first we use an analogy. Okay, chiral molecules versus achiral molecules. Chiral molecules can be very specific to the arrangement in space of atoms and elements in space within that one molecule, right? Although we just started talking about sugars, we can also apply chirality to sugars, and we're going to learn that we can use what they call Fisher projections to identify whether we have a D or an L enantiomer of a monosaccharide. And we looked at glucose and fructose uh, just in our previous video. And D is the common sugar, okay? And it's typically going to be displayed on the right-hand side when it's a linear molecule. Now remember, glucose can do something that's unique. What is that? It can be linear in solution, but also then cyclize and form a circle, just like hexane uh, and versus cyclohexane. Cyclohexane, of course, and hexane do not do that spontaneously, break apart into linear or circular molecules, but sugars do because of the unique reactive chemistry, primarily at the carbonyl carbon, whether it be the aldehyde or the ketone. They are able to be linear and be cyclized in a circle, right? So D and L enantiomers of monosaccharides, you can have glucose, D-glucose, you could have L-glucose. And when it's D, it's typically represented on the right-hand side of a linear chain. When it's L, the hydroxyl will be on the left-hand side, as opposed to D, which is right-hand. Okay, now another analogy, hands. Look at your hands. Ask yourself, can you overlap your hands exactly as they are? Well, you can put them together and they mate quite well. They match up. But if you try to put your hands over each other, put your hand over your hand, the thumbs are on the opposite side, the fingers are reversed, right? As should be. So your left hand and right hand are not completely exchangeable. If someone tried to do that, that would be horrible. Your thumb would be to the outside of your body instead of towards the inside of your body, and it'd be very confusing, like a Frankenstein horror show. So we are glad our hands work the way they do. Now going into structural isomers, we talked about that already. We're just expanding our knowledge of this because chirality is a form of isomeric definitions, but so is our past definition of structural isomers. We're going to learn that we have geometrical isomers, we have structural isomers, and we have stereoisomers that are a little bit different than structural isomers. Now, here's why. Because let's go back to our definition of a structural isomer. Um, Both of these molecules identified as ethanol and dimethyl ether both have different properties. They have different boiling points, they have different melting points, they have different vapor pressure, but the formula is still the same. They're both two carbon atoms with six hydrogen atoms and one oxygen atom. That doesn't change. What changes is the connectivity. Okay. Now the same here. We have an aldehyde and a propanone. Both of these molecules have different properties, different reactivities. The aldehyde is likely more reactive than the propanone. Maybe not by much, we don't know. All things being the same. The formula is C3H6 and one oxygen with it understood to be a one here. But both these molecules have different properties. They both have different reactivities, different melting points, different boiling points. And these are structural isomers. We learned about those earlier. But isomers, stereoisomers also have the same formula. But guess what? They also have the same connectivity, but they have a different orientation in space with respect to the elements involved. The elements may be attached to the same carbon, but oriented differently in space. None of these have chiral. There is no chiral carbon here that I can identify. Chiral carbon requires four different groups to an atom, to the central atom, which is usually carbon. We look at chirality through the central carbon atom or atoms on a molecule. And nothing here, this has three hydrogens, so all four groups that are, because only four groups can attach to carbon, right? Carbon has three hydrogens and one carbon bond here. So four different groups can attach to any carbon. We're not worried about chirality of oxygen. There's no such thing that we need to worry about here. The only point of issue with chirality is the carbon. That's how we determine chirality. So that's different than structural isomers. This is just a preview as we get into chirality. So stereoisomers not only have identical molecular formulas, they are not structural isomers because they also have they're bonded also in the same sequence. So stereoisomers are not structural isomers, and the atoms are bonded in the same sequence, which is not the case with structural isomers. But they differ in the way that the atoms are arranged in space, or they differ in the way that the elements are arranged in space at a particular carbon, and they are the same elements bound to that carbon. And if we have a stereoisomer, we have to have another molecule as a source of comparison, right? So whenever we talk about stereoisomers, we got to be talking about at least two things, if not more. So when the mirror image of organic molecules cannot be completely matched, so we're now talking about a definition of chirality. So remember our hand analogy. We could not put both our hands over the top of each other and have the thumbs line up. We can do this when they're like a mirror, like if we look at a mirror, they line up nicely, right? But if we try to put our hands over here, our thumbs end up on different sides. Why? Because our left hand and our right hand is different. They are connected the same, but they're oriented in different ways. Okay, so that is what we're going to look at when we look at carbons. It's a little different than the hand analogy, but you cannot superimpose those isomers upon each other. If you could, you'd have the same molecule. And so that's where the models come in handy, right? The models come in handy where you can actually see where the chirality in that is. If I can keep this from blurring, but you can see this as a methane gas molecule, which could be helpful. And methane is achiral. You do not have a chiral carbon on methane. CH4 has all hydrogen groups, so it's achiral, right? Again, the same review with the hand analogy. Um, when you have mirror images of molecules that cannot be superimposed, and hands are a good example, they would be chiral. But if you would have a mirror image of molecules that are identical and they could superimpose on each other, the molecule will be achiral. Okay. Um, so let's or it will be the same molecule. We must be careful there because Chirality, you have to have four different elements bonded to that carbon for it to be chiral, for it to be chiral. Chiral molecules must have four different elements bonded to the carbon. If they don't, that alone, you don't even have to worry about the mirror image, because if it doesn't have four different elements to the carbon, it cannot be a chiral molecule. We don't even have to consider it. We already know it's achiral. If it's chiral and we have another molecule that looks similar or just like it, we can do the superimposable test. If it's superimposable, it's going to be achiral. If it's non-superimposable, like the hand analogy, it would be chiral, giving it stereochemistry. Chiral molecules have rotation of light properties and really unique things that they can do. Chiral molecules are very important in drug development because you can have the same carbon attached to the same four different elements, and the enzyme will not recognize it even if it has the same attachment, if it does not have the correct orientation in space. So the orientation in space, it may have the same connectivity, but does it have the same orientation in space? Our hands have the same connectivity, right? Some examples, these examples can be good and bad because students can sometimes confuse it, but it's not meant to confuse you. You have two gloves, they are chiral. One glove is not exactly the same as the other glove. You put a right hand glove on a left hand, it feels weird. You put a right hand or a left hand glove on a right hand, it feels weird. Now, with these glasses, these are completely achiral. They're kind of undistinguishable, and you can kind of replace this glass with that glass, and no one can really tell the difference. And there is no real difference except with, damaged, nicks or something. But they're achiral. They have no, they're equivalent. There is no difference. They can both be used the same way. The shoe, though, however, is achiral for the most part. You cannot have a shoe unless they develop one that either pair works for the right or left. It doesn't work that way. You have to have a left shoe and a right shoe to properly be fitted and have the proper footwear, correct? So two out of the three here are chiral, one is achiral. And molecules are chiral when they have at least one or more chiral carbon atom. Okay. So you could have four carbon atoms, but only one of them is chiral, and it would have to be attached to four different groups. So it's always the carbon we're evaluating. It must be attached to four different groups, and it is non-superimposable mirror image. Now, it doesn't have to necessarily be four different atoms, because you could have a methyl group attached to a carbon, and then you could have a propyl group attached to a carbon. So that's different. It's a group, not just the elements. I did say four different elements. It can actually be four different groups that are distinguishable, and we'll see that. Uh, Chirocarbon will be non-superimposable mirror image, and that molecule may have different reactivity with enzymes. It may not react with one enzyme. It may react completely a different way with another enzyme, or not react at all. This is very important in drug synthesis. Let's take an example of a chiral molecule, and we might not see it initially. See how the models that I showed you can come in handy. You can make these models. You can have a carbon central hydrogen, which is going to have the least priority because it has the lowest weight. And now I talked about priority. We talked about that previously, and we can base priority of what is connected to the carbon. What do I mean? Priority is what is connected to the carbon. And hydrogen has the least priority. So of all the four, it gets four. It has the least priority. Bromine, iodine, and chlorine. Well, iodine is the heaviest, so it's going to get priority one. Bromine is heavier than chlorine. It's going to get priority two. And chlorine is heavier than hydrogen, but weighs less than bromine, so it gets three. And you could do the same here. This is one. This would be two. This would be three, and this would be four, right? So uniquely, we can get a mirror image of this when we have this molecule one and molecule two, and we can orient it so that the chlorine is facing in a mirror fashion iodine facing in a mirror fashion, hydrogen facing in a mirrored fashion, bromine facing in a mirrored fashion, just as if we would use a mirror, how things get a bit reversed, right? You can write and then put it in a mirror and you can see that the writing is reversed. So what we're going to do, we suspect it's chiral because there's four different atoms here um, attached to this carbon. There's four different atoms attached here to this carbon. And the molecular formula is completely the same. They're all the same elements, the same amount of carbon, hydrogen, chlorine, iodine, bromine, whatever. It's all the same. So there's a good chance this is a chiral molecule because we also have a mirror image. Okay. And now we try to superimpose it. And guess what? We cannot do that. We cannot. This is non-superimposable. It cannot be, I don't know, bad spelling here, but it cannot be superimposed on one another. That by default, we can get the hydrogen, carbon, and the iodine to line up, but we can't get the bromine, chlorine to line up. So that tells us we have a chiral molecule. It is chiral. Stereochemistry here is very important. We therefore have enantiomers. We don't have the same molecule, we have enantiomers. If this was superimposable and you could pop this, we'll look at the top molecule that's above, and we could switch bromine with chlorine and chlorine with bromine, then we'd have the same molecule. So you can see how the connectivity is exactly the same. It connects to the same atoms, but it's oriented different in space. And we always want to focus on what element to determine the chirality? The carbon. The carbon. I just told you sugars have chirality, but they just tend to have just carbon and hydrogen and oxygen. And you'll see, we'll talk later about sugars here in a second. But um, so you should feel confident that this is an enantiomer. They are enantiomers of each other. This is an enantiomer of this molecule, and this molecule is an enantiomer of that molecule. They're like kind of like twins, but not identical twins, right? Okay, so what if we have an achiral carbon atom and they try to trick us and give us a second um, molecule? And we have to figure out, do we have a chiral molecule and a pair of enantiomers or isomers, or do we have the same molecule? Well, automatically, we don't even really have to do this mirror test because we can look at this carbon and we see that it's attached to one hydrogen, one chlorine, and two bromine. Now, the rule is it has to have four different groups or four different elements attached to the carbon. We have only three because chlorine and hydrogen is two, and then bromine is the third. But we don't have like iodine or something. So automatically, this has got to be achiral. Okay, so if we draw the mirror image, and we can do that by just kind of drawing straight lines and interpolating where the bromine would be if we had a mirror image, and we can do that through projections used in architecture. I had the lucky break of being in architecture and design in high school. So you can line all this up here, right? You can line all this up and you can see, well, can we superimpose this? And you could. If you turn this, you could put this molecule over the top of that and everything, the chlorines and the two bromines would line up. And guess what? We have the same molecule. It's achiral. There's no, this is not, these are not enantiomers. In fact, they're the same molecule. And we can do rotation in our head. It's good if you become talented at like having an animated visual in your mind of moving things around. That's how you become a great scientist and chemist. Although AI and that is getting better at doing it, we still need a human being to interpret what's happening. So it's still relevant that you learn to rotate these molecules and see that they're exactly the same. They're the same structure. They're the same molecule. Therefore, they're achiral. They are not enantiomers, and they're the same molecule. They superimpose on each other too. We didn't have to do all that. Once we realized this was an achiral carbon atom, we knew this would not be. We knew this would not be chiral. It had to be achiral. We did the mirror test just to prove the point. Identify a chiral or achiral compound. Now this is kind of easy. It's a fun game. We have to have four different groups attached to this central carbon, right? So, but do we? Well, wait a second. We have two carbons. those are the same elements. Well, we'll get back to that. We do have chlorine and hydrogen and a methyl group. So and a carbon, we definitely have three elements. But what about the fourth? And someone might say, no, no, that's carbon too. Well, that's carbon too, as that is carbon, but these are different groups. This is a ethyl group. This substituent is a methyl group. And that's why I try to teach everybody about substituents and substituents that attach to different parts of a molecule in organic chemistry. So guess what? A is probably, it does have four different groups. It has a methyl, an ethyl, a chlorine, and a hydrogen. It is going to be considered chiral. Okay, let's look at this one, B. We have chlorine, methyl, and hydrogen. But wait a second, we have the fourth one is hydrogen. No, that means we don't have four different groups or four different elements, whatever definition we choose to focus on. It can be four elements, and then we have to go to four different groups. And if we have four different groups, we have a chiral molecule. This doesn't. These are the same. So we have to say, nope, that's got to be achiral. And we look at C and we see there's the central carbon. We only have one to evaluate. We have methyl, we have bromine, we have hydrogen, we have chlorine. So off the top of my head, we've got four different groups attached. It's going to be chiral likely. Not likely, it is. So A, B, and C, it's correct. Chiral, achiral, and chiral. So make sure you understand those fairly simple examples, fairly straightforward. What is a Fisher projection? Okay, it is a two-dimensional representation of a three-dimensional molecule. We're just going to write it flat in two dimensions, meaning we only have height, or we have height and width. We don't have any depth. We're going to place the most highly oxidized carbon group at the very top, and that's going to be, as we've seen already, we've seen glyceraldehyde, we've seen glucose, we've seen these different aldehydes and these aldoses and ketoses. And so we know that either the ketone is going to be placed towards the top or the aldehyde is going to be placed towards the top. And it is usually the most highly oxidized carbon, right? Has the most carbon-oxygen bonds. Use vertical lines in place of dashes for bonds that go back, and use horizontal lines in place of wedges for bonds that come forward. Okay, so how does that work out? Well, nicely, we can see here if we have OH and hydrogen at the central carbon of interest, they come out in a wedge, meaning they're coming out at us, the audience, in the same way here, but we have the hydroxyl on the opposite side. And guess what? Remember when I talked about D and L? This hydroxyl is on the right-hand side, so it's likely going to be a D sugar. This hydroxyl is on the left-hand side. It's likely going to be an L sugar. What else do we have? Again, we have this aldehyde, and it's the most oxidized carbon. It's going to be at the top of the chain, at the top of, towards your head, and we go down towards the bottom, and we see hydroxyl groups on every single carbon except the most oxidized carbon, as we anticipate for a very simple sugar. And we can put the mirror here, and we can do the test. Well, first, let's find out, do we have a chiral carbon here? Is this a chiral carbon? You probably already know the answer because we can't give something a D or L designation if it's not the chiral carbon. It has to be a D, a right-handed hydroxyl on the carbon of interest, or it has to be an L, meaning the hydroxyl is on the left-hand side of that carbon that is considered chiral. You can't give it D or L designation if the carbon attached is not chiral, but it is chiral here. Why is it chiral? Let's go through this again. We have a hydrogen and a hydroxyl. Those groups are different. And we have a methylene and a hydroxyl group. That's a third group. But then you might say, well, Dr. Pryor, we have a carbon here, and that's the same as that carbon. Well, it is a carbon and a carbon, but there is a different group attached. It is a aldehyde group, right? So since it's an aldehyde group, that's a separate group in itself. You remember, at first we look for elements, then we look for groups. The aldehyde is different than this methyl hydroxyl like methylene hydroxyl like group. So we do have four different groups at this carbon. We don't have that situation with this carbon because we have two hydrogens, and this one has three elements attached: to oxygen, hydrogen, and a carbon. We can't really evaluate that right now for chirality, and we don't want to. We can have the mirror image. And we see that it looks like the mirror image. And this carbon is what? This carbon was chiral, and the same evaluation process would tell us that this carbon is chiral too. So we have two chiral carbons. We have a mirror image. If we try to superimpose these on each other, the hydroxyls and the hydrogens would be on opposite sides. The aldehyde would line up with this aldehyde, and this methylene hydroxyl would line up with this methylene hydroxyl, but the oxygen would be on the side of the hydrogen with respect to comparing two molecules, and the hydroxyl would be on the side of the hydrogen with respect to comparing these two. And so these are what now this is the 3D version, but we simplify it and we do Fisher projections. This is what they're talking about, Fisher projections. So we don't have to worry about the wedges and the dashes, which can take more time if we are writing things out really fast. Scientists sometimes have to work extremely fast to beat the other scientists they're racing against, right? It can be tough, can it? Well, we look at this, and again, it's the same molecule. We can see that this is a chiral carbon. This is a chiral carbon. The hydroxyl here is on the right-hand side, so it's going to be D-glyceraldehyde. The hydroxyl in this one is on the left-hand side, so it's going to be L-glyceraldehyde. It's definitely a sugar. It's a three-carbon sugar. It's an aldehose. These might have different properties. For example, guess what? Does the body use L-glyceraldehyde? No. The body wants to use D-glyceraldehyde. It wants to use this version, this chiral sugar molecule, as opposed to this chiral sugar molecule. It likes to use D sugars in our human bodies. D and L notations are basically assigned according to the position of the hydroxyl group on the chiral carbon farthest from the carbonyl. The letter L is assigned to the structure with the hydroxyl on the left, and the very important one, because it's used in our bodies, is the one assigned with the letter D, right? So is assigned to the structure with the hydroxyl on the right. So you don't want to give people L sugars unless you really know there's some unique reason to do that. You want to give them D sugars. And now we're going to add a complication. We're going to add another carbon. So instead of a 3-carbon sugar, we're going to have a 4-carbon sugar. And remember, it says here the D and L isomers are assigned according to the position of the hydroxyl on the chiral carbon farthest from the carbonyl carbon. Well, we do have two. These are both going to be chiral. Both those carbons are going to be chiral. So we added some complication. We added an extra carbon. Um, we have D erythros and we have L erythros. But the D, let's look at the one on our right-hand side where the hydroxyl's on the right-hand side. This is the carbon of interest. This one is not giving the name. We need the chiral carbon the farthest from the carbonyl carbon, and that's not this one because it's closer to the carbonyl carbon than this one. This one is farthest away, right? So 1, 2, and 3. This is the carbon that's the chiral carbon that's the farthest away from the carbonyl. On this carbonyl here, this carbon is chiral, but this carbon here is the chiral carbon that is the farthest away. So it's got to be this one. It's got to be this one that determines the name. And here it wouldn't matter because they're both on the left-hand side, but suppose this hydroxyl is here and the hydrogen is here, and then you would name this. If you wrongfully picked the wrong chiral carbon to name this, you would end up calling it D isomer when it's the L isomer still, because this carbon was not tampered with or changed with chemical modification. So what do we have here? Indicate whether each pair is a mirror image that cannot be superimposed. So do we have a chiral carbon and therefore we have enantiomers, or do we have something else? Do we have an achiral carbon maybe? I don't know. But we look at this carbon, we see it's attached to bromine, methyl, and methylene, hydroxyl, and hydrogen. They're all different groups. This has got to be chiral. Four different groups, either groups or elements attached to this centralized carbon of interest. We're evaluating for chirality at this carbon I'm pointing to, and that is a chiral carbon. We go over here and we say, okay, this is a carbon of interest. Now, these other carbons have 4 different groups on them. They have 2 hydrogens, 3 hydrogens. That's not even a carbon. We don't have to worry about that. And that's a hydrogen. We Hydrogen's only going to attach to one bond. So carbon is chiral as well. So we can compare these two. And looking at how it's written, it kind of looks like they're enantiomers. They both are chiral, and they both look like they're all attached in the same place with different orientation, with the methyl group on opposite sides here and the hydrogen on opposite sides, with the methylene, hydroxyl, and bromine being the same. So I'm going to guess that this is a chiral. Uh, they're both chiral. We know that for sure. They've got to be enantiomers, right? But for B, we want to pick the central carbon first, and we we have 1, 2, 3. Wait a second, we have 2 hydrogens. It doesn't fit our definition. We need four. We need four different groups, right? 4 different groups to attach to carbon, and they have to be different elements or different groups, and we don't have that here, so it can't be chiral. Yeah, we have, this is a carbon to evaluate, but again, we have 3 different groups, not 4. It can't be chiral. Therefore, B has to be achiral. They're both the same molecule if we superimpose them. We can do that to guarantee that we know what we're saying, but it is these are B is a superimposable non-mirror image, meaning they're the same molecule. But A is a mirror image that's non-superimposable. So they're enantiomers and chiral. So the answer to A is yes. The answer to B is no. Okay, now we're getting into long chain, likely a glucose molecule here, sugar that we rely on for the glycolysis process where we can extract energy and feed into the TCA cycle or the Krebs cycle in the mitochondria. Very important for our energy. Not just energy, we also get a whole bunch of metabolites from the glycolysis process. We get all sorts of sugars involved there in small molecules. And we also, in the TCA cycle, we get the Krebs cycle, we get different molecules for different metabolic pathways in the mitochondria too. So glucose is super important for us human beings, right? So we got an aldehyde group here, we got an aldehyde group here, and so identify the following projection as L or D isomer. Now, we know that this carbon cannot be chiral, all right? It doesn't have 3 different groups attached to it. But this carbon has aldehyde attached to it and a long chain of carbons attached to it. So this is, it has a hydroxyl. This is a chiral carbon. And the same situation here, this is different and that's different, and the hydroxyl is different and hydrogen is different. That's a chiral carbon too. And we look at this, this is a different group compared to this. So there's 2 different groups, the hydroxyl and hydrogen. That's chiral. We look at this carbon, we got this huge chain there, and then the methyl hydroxyl, then another hydroxyl and a hydrogen. So these groups are different. Although they're the same elements, they're different groups. We go to this carbon, oh, we have 2 hydrogens and a hydroxyl. This cannot be chiral. That's achiral. This cannot be chiral. It's achiral. So we have 4 chiral carbon atoms here where we can have a D or an L designation. But remember, the L or D designation goes to the chiral carbon the furthest away from the carbonyl or the most oxidized carbon, which is the carbonyl. So we have to say, well, that's chiral, that's chiral, that's chiral. Ah, this is the most far away. That's gotta be how we name it. And so we therefore, since the hydroxyl is on the right, we know that has to be D, which is what the human body could use. Well, this molecule looks really similar. The hydroxyl's on the same side. This cannot be a chiral carbon. This is a chiral carbon. This is a chiral carbon. This is a chiral carbon again. This is achiral. So we know that the chiral carbon, the furthest away from the most oxidized carbon or the carbonyl in a sugar, has to be what the name comes from. And this is on the left-hand side. This has to be some kind of L sugar. And so how does this work out? Well, the hydroxyls are on the same side for this carbon. The hydroxyls are on the same side for this carbon. The hydroxyls are on the same side for this carbon. But in this case, the hydroxyls on the right-hand side or becomes D, and in this case, the hydroxyl's on the left-hand side, it becomes L. Everything else looks the same. My guess is we do have an isomer. We have a stereochemical isomer here, if not an enantiomer here, um, which is basically somewhat like a what? Mirror image almost? Well, there's a lot of sugars because remember, we can go here and change all these hydroxyl groups. We can switch one and we can get multiple isomers. We can have 8, 10 different molecules, for example. So it may not be an enantiomer, but all things being even, it is a stereoisomer, and one is D and one is L, and we can feel confident. And it pretty much it is a stereoisomer in the fact that this would overlap except here. So they're non-superimposable mirror images. You cannot superimpose these. And you really can't say they're mirror images because the hydroxyl here would have to be changed, and the hydroxyl here would have to be changed, and the hydroxyl here would have to be changed if we were to draw a mirror. So they're not even quite isomers. Maybe it'll turn out that they're diastereomers. But which one of these does our body use? And you should say our body uses D sugars, and this is a D sugar. Forget all these other designations. We need to worry about the carbon that's the farthest away from the most oxidized carbon or the carbonyl in the molecule, and that's this one. And what did I do here? What did we do here? We have linearized, we've made linear the glucose molecule. The glucose molecule is often in a cyclic form. We're showing you the linear form here to evaluate these Fisher projections. And then you have all sorts of lines here where you have hydroxyls and things like that coming off here. And you have the hydroxyl here, and then you have a hydroxyl here, and you're able to you have hydroxyls all over the place here, and maybe a CH, and so eventually when you start doing any biochemistry, you'll need to learn more about this, but this may be enough for this class. So this can linearize. This D, this hydroxyl here, I'm just going to tell you that what happens is it comes over here and attacks that carbonyl to form that circle. And then these electrons flow up here, and you cyclize this molecule. And this happens, they go back and forth from a cyclic structure to a linear structure, to a cyclic structure to a linear structure in the human body. One enzyme can process the circular sugar molecule, and one enzyme can process the linear molecule, and there could be many more than just one enzymes. And the majority of the time, the sugar will look like this. It'll be in a cyclic form. Now, you're not going to have to memorize the structure per se. You can put it on your 3x5 index card. Okay, so moving on, we were able to identify this hydroxyl, the farthest from the carbonyl, as we just did, is going to tell us it's the D isomer. This one is on the left, therefore it's the L isomer. And that is how we look at Fisher projections, which are just linear and not cyclic. As what molecule are we looking at again? We're looking at glucose. This is glucose. Both molecules are glucose, but one is the D isomer that we use, the L isomer that our body doesn't use. Okay, so biological systems depend on chirality. Enzymes, for example, and not only just enzymes, but enzymes and cell surface receptors, which use to help signals from cell to cell, just like we get mail in our mailbox to get information from other people outside of us. Enzymes and cell surface receptors care about chirality and stereochemistry and enantiomers. They all tie together. Enantiomers, stereochemistry, chirality, right? So metabolic reactions require chirality sometimes in a way to distinguish a molecule. And only one enantiomer will interact with an enzyme in many cases. Only one enantiomer, right? This is very important in drug synthesis as well, right? So, and the chiral receptor fits the arrangement of the substituents to only one enantiomer. So it may only attach to the D isomer and not the L isomer of glucose, right? So here's a good example of just a single carbon with four different groups attached to it. A single carbon with four different groups attached to it. So it's definitely chiral. That's chiral. That's chiral. But what might different, even though it is a chiral molecule, the groups are attached all in the same arrangement or the same way. They're all attached and connected in the same way, but their orientation in space, the 3D space differs, right? And we can see if we draw the line here, we could see that this is a mirror image. This is a mirror image. And they're all four, and we cannot superimpose this molecule on that molecule. So it is chiral, it is an enantiomer, they're the same formula, everything, same connectivity, but different orientation and respect with the attachments. And guess what? We have a chiral receptor on an enzyme surface. So a receptor, chiral receptor on a large enzyme. So this will dock on that enzyme and maybe activate it. This will activate the enzyme because everything fits perfectly in space and all the groups can attach to the chiral receptor on the enzyme and activate the enzyme, cause the enzyme to be activated, making it work. But here, the shapes don't match up. This molecule cannot stay here at this site. So the enzyme does not get activated, right? Or shut off, because sometimes docking molecules can shut off an enzyme, or sometimes docking molecules can turn on an enzyme. It can be a switch that works different ways for different molecules and different enzymes. So very unique biochemistry. Chirality is very important to biochemistry and biological systems, biological chemistry. Interesting. Now we have and we have this L-DOPA. This is a neural receptor. This is a neural, should I say, a neurologically activating chemical, and we use a substance used to treat Parkinson's disease is L-DOPA, which gets converted. This L-DOPA gets converted, I think, directly into dopamine. Okay, so there's like one step to get to dopamine, maybe. And this is in our brain. We need dopamine. Dopamine can help raise serotonin levels. So we have L-DOPA converted to dopamine, and dopamine somehow activates something that raises a serotonin level. So that's a complicated system, sort of, right? So you got three things involved, and we're not even giving you all the details. This is challenging even for a guy like me. So we have an enantiomer, D-DOPA, we have D-DOPA, and we have L-DOPA. And now guess what? They're telling you that the L-DOPA is necessary. Now remember, this is not exactly a sugar molecule. It's a little bit like a sugar molecule, but L-DOPA is not a sugar molecule. So this does not have to be a D like with sugar. There's a new rule here. For this one, for this particular hormone-like substance that gets a neural activator, neurochemical, um, it's L-DOPA that we need. We don't necessarily want the D-DOPA. For example, the enantiomer D-DOPA is not effective for the treatment of Parkinson's disease. So what do we have to look at? The chiral carbon, which is the asterisk here. That's the chiral carbon right here. There is no, well, this is close to a chiral carbon, but it's not. This is not. This is the only chiral carbon in the molecule. And L-DOPA is what the body requires. We need L-DOPA. If we accidentally give the patient D-DOPA, which if it was sugar molecule, it'd be fine, but we need to administer L-DOPA for the Parkinson's diseased patient. So we don't want to give them D-DOPA, we want to give them L-DOPA, right? So we got to be careful of not just generalizing, oh, D sugars, therefore that means everything uses D enantiomers. No, it could be a total different molecule, and this is a different class of molecule. Although it's like sugar because it has hydroxyls here, it has a flat benzene-like ring that's aromatic. Sugars typically don't have that unless you do some modifications. It has an amine group, almost like an amino acid, right? So maybe this came from an amino acid. Maybe it came from phenylalanine or something, I don't know, or phenol-like amino acid. You can look that up, and was synthesized metabolically, but it's not this one. It's not D-dopa. Our body doesn't tend to use D-dopa the way it does L-dopa. It may not use it at all, so we don't want to give the patient that, which is the opposite of what we learned about sugars. That's amazing. For many drugs, only one of the enantiomers is biologically active. Now, it could be possible the enzyme may recognize both, but not always, right? So for many years, drugs were produced with mixtures of enantiomers, and it was kind of a waste because the one enantiomer was worthless and the other one was effective. So you really got half the dose of what you thought you were getting. So today's, or maybe not exactly half, because some enantiomers are easier to make than its isomer, than its partner, its other enantiomer. Okay, so um, today's drug researchers definitely use chiral technology to produce the active enantiomer of chiral drugs. Very important if you go into pharmacy. Now that ends it, everybody. Um, I really appreciate your time. I hope you got a lot out of this. I'll see you again.